we get to summarize in this lesson really the sum total of many people's life's work over literally thousands of years, because ever since antiquity, people have been looking at what the universe is made of around us and trying to figure out what the universe is actually made of. And so we would do thought experiments, thousands of years ago, the ancient Greeks and so on, to try to figure out, well, what would happen if I take a block of matter and I cut it in half, and then I take that and I result and I cut it in half, and I keep cutting it in half over and over and over again. Will I eventually get to a fundamental building block of matter? And the prevailing idea at the time was that yes, you eventually would, but we really didn't know exactly what that looked like. And so eventually time passed, experiments were passed, we learned that we could take different substances and do what we now call chemical reactions, and we have an atomic theory of matter put forth by Dalton and others in the 1800s, and that basically said that everything is made of these things called atoms, and all the substances that look so different around you really are just different combinations of atoms. Kind of like a little Lego set, you put them together in different ways, and then of course you have different properties. So you can take carbon, which is, after you burn you burn some wood or something, you have just the carbon left behind, or you go in deep underground, you get some carbon out of the ground, a charcoal-looking substance, right? You take some oxygen, which is a gas, and then you burn those together, and you can produce carbon dioxide, which doesn't look at all like the carbon that it comes from, but it contains carbon, right? You take hydrogen as a separate example, which is a colorless, tasteless gas that's flammable, and you have oxygen, which is another colorless gas, and you combine them together, and the result of the combination doesn't look at all like hydrogen or oxygen. It is called water, and it's a liquid. It's not a gas at all, and we drink it and we use it to dissolve things and drink our tea, but it doesn't seem to have any of the properties of what it is made of. Well, of course, the reason is because once we combine the atoms together into molecules, then the shape of the molecule, the way the electrons that we now know exist, are distributed throughout that molecule. It governs everything about that molecule. How it boils, how it freezes, the mass of the molecule, the color of it, all of that stuff depends on the shape of the molecule, the electrons, and the geometry of whatever it is. So you can take different types of atoms, combine them together in different ways to make basically every substance that you've ever seen in your life, including everything that you are made of, right? Because long time ago, people thought living creatures were very special and made of different stuff, different bits of matter that was allowed to be animated with the soul and things like this. And so, but now we know that you are made of these same things that is in a block of wood, the same fundamental building blocks called atoms, right? And so we had that atomic theory. But it took a long time to figure out what the actual atoms were made of on the inside. We call that the realm of the subatomic. Subatomic meaning smaller than the atomic, right? And in the last lesson, we talked about the discovery of the electron. We said and talked about how that was discovered using cathode rays and Millikan's oil drop experiment. So if you haven't looked at that, go look at that, and you will see how the discovery of the electron came about. So now it's time to turn our attention deeper inside of the atom into the core, which we now know to be called the nucleus. But for now, just erase from your mind that you know what you think you know what an atom looks like, because believe me, even if you think you don't know what an atom really looks like, because none of us do. Even me, I have my own mental image, but it's not really like what an atom really is. Anybody that tells you they know exactly what an atom is, or they have an exact understanding of quantum mechanics, is lying to you, because nobody truly understands actually quantum mechanics. I mean, we understand the math. I'm not saying people don't know the math. I'm saying the quantum realm, the small realm, is so different and divorced from our everyday experience that none of us have common sense when it comes to quantum mechanics. So we have to build models, and we try to see if the models that we build correspond to what experiments we perform. And so we have the early models, and now we have the more modern models, okay? So let's erase what you think you know about the atom, and let's go back in time to the year 1896, where scientists were looking at different elements that they were getting out of the ground and other places, and they came across an element called uranium. Now, I know that you know that uranium is associated now with what we call radioactivity, but at the time they didn't know any of that, and they just noticed that this uranium was emitting something from it, right? And there was a lot of experiments done with that uranium and also with other elements, because what you find is that when you put what we now know to be a radioactive piece of rock next to a film, a piece of film, even if the film is enclosed, like a film for a camera, inside of a dark sealed container, it turns out that because the film is usually exposed by light, actually the radiation coming from these radioactive elements can expose the film. And Marie Curie and other people figured this out. So they deduced and surmised that somehow, even though we can't see what's going on with our eyes, there must be something emanating from some of these substances, which we now know to be radiation, radioactive decay. And when, of course, the radiation hits the film, even if the film is inside of a sealed container, it appears that the radiation can go through the container into the film and expose the film. And so we started doing more experiments with that, and they discovered in 1896 that uranium emits high energy radiation. So what they wanted to figure out is, okay, what is coming out of this uranium? Let's go study it. So we did some experiments. And the kind of experiment they did is something like this. Now the real experiment is much more involved than this. Of course, I'm just drawing a little picture here, right? But they basically just created a block of lead here. So this is a lead block. And the reason they chose lead is because they figured out through trial and error, because the radioactive material can expose the film, which is separated from it. If you put different things between, it seems to do a good job of blocking the radiation. Even paper, just a sheet of paper, can block a small amount of the radiation, but actually lead seems to block a lot of it. Now we know the reason lead works so well is because it's a very heavy element with a very big nucleus and so on, and it can absorb some of the radiation and basically block it. So what they do is they build a lead block here to prevent the radiation from leaking out from any other side. And then way on the inside here, they put a sample of some rock that they've collected, which could be uranium or just any other radioactive material. So I'll just put radioactive. Okay. And because it's inside of this block, everything is absorbed in these directions. The only way in which the beam can go, or the radiation can go, is down this long chamber right here. And so basically the radiation just flies out in this direction. And what they do is then way down over here, we put a screen, some kind of screen here. And that's probably not the best picture. Let's do it like this, some kind of little screen that it can hit, right? And this could be a fluorescent screen like we talked about before, in which case when it impacts, you'll see a glowing little spot there. But anyway, some sort of detector, some sort of screen right there. All right. Now, what we figure out is that the radiation travels, it has to travel down a straight line because, of course, it's surrounded by lead. Any rays that hit up here are going to be absorbed, and so it can only go straight, and so it's going to hit the center part of the screen right here. And what we do is actually in between the source and the detector, we put a couple of charged plates. So we put a little plate right here, and then we put another little plate right here. And so the beam has to travel between the plates. And one of these plates, this is hooked up to a circuit here, one of these plates is charged positive, and one of these plates is charged negative. Now I have not drawn the rest of the circuit here, but this line comes up to a battery or something, and it goes down and connects here. And so it's literally charging up those plates. We now know that charged plates it's charging up because of electrons, okay? But they didn't really know exactly why the plates were charged, but they knew how to build batteries, and they knew that if you hook them up to plates, you could get a large surface area of what we call electric charge, right? Even if you don't know what's doing the charging, you know that the result of that can create some charged plates. And so it turns out that when you do this experiment, the following happens. Well, sometimes, I should say a part of the beam goes straight ahead, straight down this way, and it impacts right here. And that's exactly what you might expect. And so one of the beams, or part of the radiation, there's lots of different kinds of radiation coming out from this thing is what I'm going to lead up to. And some of the radiation just is completely unaffected by the positive and negative plates here, and it lands over there. We call this gamma radiation, or gamma particles, if you want to call it that. So we use a Greek letter gamma. I know it looks like an upside down ribbon, but that's a Greek letter, lowercase gamma, right? So we call this gamma particles, right? But then it also turns out that some of this beam splits up, and actually once it gets to the plate area like this, it begins to curve up pretty dramatically and goes up and impacts something like this. So the beam kind of splits off, where part of the beam goes straight ahead. We call those the gamma particles. Part of the beam comes up here. We call this the beta particles. This looks like a bee with a little hook at the end, a little tail at the end of it. That's a Greek letter beta. Okay, and then it turns out that there's another class of particles that comes and is bent down. It's not bent as much, but it is bent down right here, and we call this one, I'll kind of draw a little arrow right here, we call this the alpha particles. So it turns out that the story goes that basically they determine, hey, this radiation, this invisible beam is coming, particles or beam or whatever it is coming out of these things we call radioactive material. Let's figure out what they are. We'll pass the beam through some charged plates. And it turns out that it's not just one species of radiation. It turns out there's 3 different little subclasses of radiation in this particular experiment that they were able to detect. One species of whatever the stuff is goes straight ahead, completely unaffected by the charged plates. That means whatever it is must not have any electric charge. Because remember, we know that like charges repel each other and opposite charges attract each other. But if you don't have any charge at all, then you're unaffected by you're not attracted or repelled by an electric plate like this. So whatever this beam is that we call the gamma particles, it's not a charged beam because it doesn't deflect at all when it goes through the plates. But then we have another beam that is pulled strongly up. Notice how far it is pulled up. We call those the beta particles. And whatever the beta particles are, they must be negative particles because they're attracted to the positive plate. Remember, opposite charges attract. So it must be a negative particle that goes up like this. And then whatever this particle is down here must have a positive charge because it's bent down and attracted here. So positive would be attracted to negative, and it lands over here. So we know that this must be a negative particle, this must be a positive particle, this must be a particle with no charge, and we can also tell because of this particle is basically deviated or skewed so much that it must have a very small mass, and this must have a big mass, or the amount of charge on those objects is grossly different from one another because one of them is very strongly pulled up. So it could be because it's a low mass, able to be deflected easier, right? Or a very, very, very strong charge on the particle. Or the same thing could be happening for what's going down over here. So I'm going to cut to the punchline because there's a lot of experimentation that basically happened to allow them to try to figure out what these things are. So I'll cut to the punchline and show you what we now know to be the case and how it explains everything above. What we learn is that the gamma particles are, these are called gamma. And they're really, everything in quantum mechanics, you can think of it as a particle or you can think of it as a wave. Even light, we all know to be light waves, right? We usually talk about light being a wave, but actually light is also a particle. It's called a photon. A particle of light is called a photon. So everything that you talk about, you can think about it being a particle or you can think about it being a wave. So if I refer to gamma being a particle, it's just that every electromagnetic wave, which is what a gamma radiation is, or light also. Radio waves, microwaves, gamma rays, what else do we have? You have infrared, you have all kinds of things. They're all electromagnetic waves, but we can also consider them to be photons, which we'll learn about much later when we talk about quantum mechanics. Every light source you've ever seen consists of a stream of photons, which has a wave nature and also a particle nature. If that bakes your noodle a little bit up here, if you can't visualize that, join the club. Quantum mechanics is weird, and we're going to get there. We're going to try to understand it. But for now, just know that gamma, I may call it a particle, but it's actually more closely related to high energy electromagnetic, that's EM radiation. Like an X-ray. It's like an X-ray, except it's even higher energy than an X-ray. So this, even though you can think of it being a stream of particles, it more closely resembles a wave, a high energy wave that looks more like an X-ray. Okay, so that's what the gamma is, and that's why it's not deflected by the plates, because it doesn't have any charge. It's just an electromagnetic wave that travels, and it comes out, part of the radioactive decay of uranium and other substances can yield gamma particles or gamma waves or gamma rays, however you want to refer to them, but it's electromagnetic radiation, and so it doesn't have a charge to it. All right? And then we figured out that these beta particles right? These beta particles were what we now called electrons. And the way I'm going to write an electron is an E with a little negative there. The negative just reminds you the electron is a negative, right? And we now know that the charge on an electron is equal to -1. Now we know that the charge of an electron is -1, so it's a negative charge, so we know that it's going to be attracted to the positive plate, and that's why the beam is skewed up when it hits the detector like this. So it has a charge, whereas the gamma rays don't have any charge at all. And then finally, we have the alpha particle, and this was the one that's a little harder to explain, but I will tell you that we now know that the alpha particle has a charge, an alpha particle has a charge of +2. So whereas an electron is -1, an alpha particle is a charge of +2. And you might say, well, wait a minute, I thought we were learning about protons. I know protons, I know what protons are, but I don't know what an alpha particle is. Well, nature is not so nice and tidy. I'm sorry to break this to you. Sometimes we have to accept that what nature provides us is what we have to learn about and study. When these things decay, they don't just decay in a stream of protons that comes out of the nucleus. What actually happens a lot of times is they decay alpha particles, which I will tell you we now know that an alpha particle is equal to the following. It's 2 protons and 2 neutrons, kind of stuck together as one unit, right? So you can think of it as like 2 protons and 2 neutrons. So I'll put little pluses here in the protons and 2 neutrons. So it's like a unit, and it's like a nucleus. It's like the nucleus of an atom with no electrons that are around it, but it's traveling together as a unit. They're bonded together with a strong nuclear force. Now, I know we're in a chemistry class, so we haven't talked about nuclear forces, but I guess I'll say as an aside, have you ever wondered if we know that positive like charges repel, right? And we know that opposites attract, then all electrons should repel each other because they're like charges, and all protons should repel each other because they're all like charges. And I also told you that the electric force, which is the force between these charged particles, is millions and millions and millions and millions of times stronger. Remember, 10 to the power of 39 times stronger than gravity. It's incredibly strong. So how could you ever have a particle that's stuck together like this when you have 2 positive charges right there? Wouldn't the nucleus or wouldn't this particle try to just immediately rip itself apart? Because both of these charges, the positive charges, are trying to push and repel each other. Same thing is true of any atom. If you go up in the periodic table, lithium and beryllium and carbon and oxygen, we're going to learn as we go through the periodic table what's happening is we have more protons and neutrons in the nucleus. We also have more electrons surrounding the nucleus. And as you go down the periodic table, the nucleus is getting bigger and bigger and bigger and bigger with more and more and more protons. And if the protons are all trying to repel, how in the heck can the nucleus stay together? Wouldn't it just try to rip itself apart? And the answer is there's another force of nature that you don't learn about until usually you get to university, and that's called the strong nuclear force. It's because it's the nuclear force, but it's stronger than everything else, right? It's stronger than the electromagnetic force. So you remember how I told you the electric force was millions and millions of times stronger than gravity? And I tried to blow your mind with that, right? Well, the strong nuclear force is actually stronger than that by millions of times. It's actually even stronger than the electric force. So basically there is an attractive force inside the nucleus that we call it the strong nuclear force that is holding this thing together, and it's even stronger than the repulsion happening here. So that is how the nucleus stays together, because there's another force of nature that's holding it together called the strong nuclear force. But the catch is the strong nuclear force is stronger than the electric force, but it only acts over a really, really small distance. Like, it only acts inside the nucleus. It doesn't have, like gravity can act between planets, very long distance, right? Electric force can act very long distance. Magnetic forces, very long distance. But the strong nuclear force is stronger than all those, but only over incredibly short nuclear distances. After that, the force goes to 0. So this is what happens. You add more protons and neutrons, nucleus gets bigger. Add more protons and neutrons, nucleus gets bigger. As you do that, you keep going down the periodic table. You eventually get to lead, you get to mercury, you get to these very, very heavy elements. And as you add more and more and more protons and neutrons, the strong nuclear force is trying to hold it all together because it's stronger, right? But eventually, if you add too many protons and too many neutrons, then what happens is that strong nuclear force, it's not strong enough anymore because it only acts over short distances. So if you make the nucleus too big physically, then it starts to become weaker than the electric force, which is trying to blow it apart. And that's how you get radioactive elements near the end of the periodic table. They all exist near the end. Uranium, plutonium, radium. There's a bunch of radioactive elements near the end. And the reason that they're radioactive is because when you try to build an atom with a nucleus that's too big, then the strong nuclear force can't hold it together anymore, and the electric repulsion of the protons end up making that unstable. And a certain fraction or percentage of those atoms will spontaneously decay, which is what we're talking about here. Uranium is a radioactive element. Because the nucleus is so big, statistically, they're all not going to hold together. They're not all going to decay at the same time. So over time, you'll get the steady stream of particles coming out. And what they discovered is that in uranium, or in this experiment here that they performed, we had the three kinds of particles. We had the alpha particle, which is a conglomerate of actually 2 protons and 2 neutrons. And what we discovered about this, or what they discovered about this, is that not only does it have a charge of +2 because it has 2 protons. Remember, the neutrons have no charge, so the charge of the alpha particle is +2, but it was about 7,400 times the mass of the electron. So it's way more massive, and it has more charge, right? And because of that, because it's +2, it is more strongly attracted to this negative plate. But it's so massive, it's like trying to move a train. I mean, if you walk up to a train and try to change its direction, or a spacecraft, try to change its direction, you have to apply a lot of force because it's so massive. This alpha particle, the protons and the neutrons, is so much more massive than the tiny, tiny little electrons that we have that, yeah, even though it has more charge, +2, it's harder to change its path, right? That's why the alpha particles they do deflect, but not nearly so far, and they only go down a little bit. And then we have the beta particles. So the alpha particles were the positive ones that get deflected a little bit. The beta particles we now know to be electrons, and electrons have a -1 charge, right? Each proton has a +1, so you have 2 of them. You have a total of a +2 for the alpha particle. The electrons are equal and opposite in charge from the proton, so you have a -1 charge. And the mass of the electron is much, much, much less than the mass of a proton or a neutron. It's thousands of times less. So most of the mass that we have in an atom, we always say it's concentrated in the nucleus. Not only because the protons and the neutrons are jammed into the nucleus, but because the protons and the neutrons just have more mass by thousands of times. The electron is just not very massive. So the mass of the atom is all concentrated in the nucleus because the electrons don't have much mass. And of course, they're spread out also, we'll talk about here in a little bit, whereas the nucleus is concentrated. So we have the alpha particles with +2, we have the beta particles with -1, and we have the gamma particles, which is really we call gamma radiation, which has no charge at all. And that explains this. So they started saying, we have this piece of matter, and we've discovered not 1, not 2, but 3 different kinds of particles coming out of it. One of them has no charge at all, that's gamma. One of them has positive charge, one of them has a negative charge. So, can this be a clue as to how the atom is constructed? Shouldn't these types of particles be living inside of the atom? How are they arranged? How does it work? And so a lot of people did a lot of work trying to figure out, based on knowing what these particles are, and maybe putting forth some theories that maybe this alpha particle consist of smaller particles yet, which turned out to be true. How can we put forth a model of the atom that makes sense? Now, the first and the most prominent model of the atom, I'm telling you here in the beginning, education is a series of lies. One of my favorite professors told me that. And so I'm going to lie to you a little bit. I'm going to tell you what people thought at the time, and then I'm going to tell you the modern theory of what the atom really is, okay? But in the early days, people thought that this arrangement of these little particles that we've discovered here resembled plum pudding, okay? So they call it the plum pudding model. So what they said, I guess I'll just write down plum pudding model. And this is the early 1900s. I want you to stop and think about that. Early 1900s was just over 100 years ago. We didn't even know what an atom was. And now we not only know what an atom is, even though we don't really know, but we know a lot more about it. That we can build lasers and computer chips and all these things. We could not do those things if we didn't understand what an atom is. So if anybody tells you, I don't even know why we learn about science, why is science so important? Well, if we didn't understand atoms, no computers, no transistors, which are how computers are built, no computer screens, no screens of any kind, no iPads, no iPhones, no nothing, no radio transmission, none of that stuff. If we don't understand how atoms work, which is what these people figured out, none of the follow-on applications can ever happen. So I roll my eyes when people are like, why do I have to learn this? Well, I hope you enjoy modern life because it's all because of people figuring this stuff out. So they figured out the plum pudding model, which we now know to be completely wrong, but it was a good idea, right? What they basically said is maybe the atom is just a blob, a circular blob, which is mostly comprised of the positive charge distribution. So most of the mass, basically they said, well, the positive charges look like they're much, much, much more massive than the negative charges. And so maybe, we know that lead and gold and mercury are very heavy, so maybe the mass, which is the positive charges, are all evenly distributed throughout what we call the atom. And so this whole area, which we call the atom, is basically I could put little pluses everywhere. I could put little pluses all over the place, like this. But basically the bulk of the material is just the positive charge sitting there. And then these negative particles, which we have also discovered emanating from these atoms, these negative things, which we're going to call electrons, plus we actually can create them cathode rays. Remember, we talked about that in the last lesson. Maybe they are just also kind of distributed. I'll do that in red. They're distributed throughout, so I can just like put some red dots. It's like plum pudding, right? So you make some pudding and you just put these little raisins in the pudding, and that's called the plum pudding. And so you can say here, the electrons are distributed also. I'll just put electrons are distributed. So basically it was called the plum pudding model because the positive charges, which are more massive, were evenly distributed and evenly mixed around with the negative charges, and that whole arrangement is what they thought the atom was. So the next step is, all right, this is your model. Now what you have to do is go create some experiments and see if you can test your model. And so that's exactly what people did. Very, 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 very smart people. All right, so what a gentleman by the name of Rutherford did shortly after this plum pudding model was put forward and thinking about it is how can we test it? Basically what they did is they put atoms as a target. They used gold foil as the target. They use gold because it's a very heavy element. We think there's a lot of mass there. And they start shooting things at the gold foil. Specifically, they start shooting these alpha particles because we can generate these alpha particles with these radioactive materials, and we accelerate them and we shoot them and literally just try to, it would be like taking a rifle and just shooting a block of wood and see what happens. Does the wood blow up? Does the wood splinter? Like what happens? Let's do the same thing on a smaller scale. So what we do is, or what they did, is they construct an experiment. So what they do is they come over here and say, all right, this is an alpha particle source, right? It's like a little gun, essentially. And then what we have is a target. So I'm going to put a target right here, right? And I'm going to say gold target, right? And so basically what's going to happen is they're going to hit. These alpha particles are going to come and they're going to collide with the atoms that are inside of the gold target. And then what we have is we have a detector, which I guess I'll change colors for that. We have a detector which goes all the way around the target. And this detector, we're able to see what happens to the alpha particle. Where does it land? Okay, do the alpha particles go straight through the target and land straight behind? Do they bounce off some of the gold? Where do they land? And you're probably thinking, well, you just hit a sheet of gold, so maybe they just stop. Well, yeah, a lot of them are going to stop, maybe get embedded in there, but a lot of them are going to ricochet and bounce off the little atoms that are in there because it's a very thin piece of gold. And also, these alpha particles, you accelerate them very fast. So it really is like a rifle shooting a bullet, but much faster even, and it hits that gold there. So where are the alpha particles going to go? Remember, these alpha particles are very massive. I mean, the alpha particle is 7,400 times the mass of an electron, so they're very massive. It really would be like shooting a cannonball, into, I don't know, some bushes or something like this. So where do the things go? Well, you shoot this beam at the target, and what you actually find is a lot of them do go pretty much straight through. You might expect that. Imagine if you had some tissue paper some tissue paper and you shoot a bullet at the tissue paper. Well, it's going to go right through the tissue paper. You have a very thin sheet of gold, I mean very thin, and you have this very heavy particle. You accelerate it very fast. You expect most of the particles to go right through the foil, and that's exactly what happened. Maybe there's a little bit of it kind of going up or going down because it's interacting here and it ricochets up or ricochets down. Maybe some of them do go straight ahead. But what actually happens is some of them actually get scattered to these wider angles like this, but that still sort of makes sense. I mean, you might expect that some of them are going to interact with the gold here and bounce up or bounce down. But what actually ends up happening is weirder than that, because some of these things actually get scattered to very wide angles like this. Some of them, not too many of them, but some of them, right, go way out here. You would not expect a very heavy bullet to hit a sheet of paper and bounce up like that if you just shot a bullet at something, right? But here's the weirdest thing. Some of the bullets, the alpha particles, actually bounce backwards like this. And they bounce backwards towards the detector. Now tell me, how would you explain that? Think about it. You're shooting something very massive. It's very small, but it's very massive at a very thin sheet of foil. It literally is like shooting a bullet at a piece of tissue paper, and some of the bullets bounce back towards you. That would be astonishing. That's actually the exact analogy they used. And when they got these results, they said it reminded them of shooting a bullet at a piece of tissue paper and the bullet bounces back at you. So your plum pudding model doesn't seem to make sense. Because if all of the positive and negative charges are evenly distributed, then we would expect that most of the positive charges to go straight through, maybe bounce up, down a little bit. Because these positive charges are kind of evenly distributed, the particle you're shooting at it is also positive. It's an alpha particle. And so, yeah, you expect it to be repelled, but you also have the electrons in here, which are attracting it. And so you would figure that most of them would go right through. Or most of them will be maybe ricochet and have a very slight little angle that they kind of like bounce off of when they hit that detector. How is it possible that such a heavy, massive positive object bounces backwards towards you? And so because of these experiments, directly because of the experiments, the modern idea of the nucleus of the atom was actually proposed and put forward. And that's what we, of course, think and we know that atoms are, basically. So they put forth a new theory. So I'll say atomic nucleus. Because before this, everybody thought the protons and the neutrons, they were just kind of all mixed together, right? But that can't be the case. So what they did instead is they said, well, maybe the positive charges, which are really massive, are concentrated in the center. And basically the electrons are, kind of going around, maybe not even orbiting around, but maybe they're just kind of surrounding because they're much less massive. And so maybe there's a lot of empty space here where the mass of the atom, instead of the mass of the atom being like evenly distributed throughout the atomic size, maybe most of the mass of the atom is in the middle, so massive. Because the protons and the neutrons, which I have to admit, they didn't know about the neutrons yet. But anyway, they figured out there was neutrons in there too. The massive part, maybe that's all in the middle. And surrounding that is the electrons, which are just not very massive, and they spread out, and so there's just not that much there. And maybe the atom is actually mostly empty space. And maybe that is why most of the particles go through. But occasionally, when one of these particles actually, so a particle might go, I guess I'll draw some more pictures here. If you have a situation like this, right? How could the particles react? Well, if a particle is shot through the empty region, it goes right through. Particle shot through this empty region, it just goes right through. That explains why the beam does go through most of the time. But maybe occasionally, one of these times, the particle goes right next to the nucleus and it bounces off at some angle like this. And this explains why we have some of these high angles, because if the mass is concentrated in one point where all of the positive charge is very concentrated near and remember, gold's a heavy atom, so there's a lot of positive charge in the center of the atom, then that would provide a repulsive force. You're shooting a positive alpha particle at a positive nucleus. If it gets really close, then it's going to strongly ricochet off, and you might get some situations where it bounces up high. And you might even get some situations where, what if one of these things comes in at an angle like this and just direct collision with the nucleus, maybe it bounces back towards the detector. And that's exactly what we see here. So what they basically said is, because most of the particles go through. Maybe the mass of the atom is mostly empty space, but occasionally one of these particles will hit the very tiny nucleus, either very close, in which case it ricochets highly, or a direct hit, in which case it comes right back towards the detector. And that experiment was basically the genesis of modern atomic theory. The idea that the nucleus contains the positive charges, the protons, and of course now we know neutrons live in the nucleus also, which have no charge. Surrounding that is mostly empty space, but also these negatively charged electrons, which, remember, electrons don't have very much mass. They're not very mass at all. The mass of everything that you know, everything you've touched, everything you tasted, everything you've eaten, it's all concentrated, almost all of it, in the nucleus by thousands of times, because electrons just don't have very much mass. All right, so to wrap it up, after all of this and subsequent experiments that followed this, the discovery of the electron happened in 1897. That was when the paper was published about the cathode rays and about the electrons, which we called the cathode rays in the beginning. The proton was discovered in 1919, or formalized, after these experiments with Rutherford and with the alpha particles. And the neutron took a while longer, because the neutron's harder to detect because it doesn't have any charge. It has a mass. Protons and neutrons have about the same mass, very close, but the neutron has no charge. And we figured out in 1932 that neutrons existed. So literally less than 100 years ago, we didn't even know that neutrons existed at all. All right, and now here is where I go down and tell you about the modern, I guess I should say, the 4th grade version of what an atom is. I'm going to draw a picture of that. We're going to talk about this a lot in the next lesson also, so I'm going to repeat myself, but I want to break down your barriers. I have to break your barriers down, because I know you're watching this and you're thinking, I know what an atom is. I've seen pictures of that. Well, you don't. Trust me. Nobody knows what an atom is. Anybody that tells you they think they know what an atom is wrong. They don't. Nobody does, because it's a quantum object, and none of us can really interact with quantum objects on a one. I mean, we touch everything. Everything's quantum, right? But I mean, an individualized single atom is a quantum object, behaves differently than the large things around you. So none of us have direct experience with what they really look like. So after these things, and we realize the center of the atom contains the positive charge, the mass of the atom, we wrote down the following model. The following model, which was used for many, many years, and it's still what is taught in 4th and 5th grade, around the world, or younger even. Basically, in the center of the atom, you have these things called protons, and you have these things called neutrons. So let's say you have 2 of these protons, which are positive charges, and you have 2 other particles called neutrons, which are no charge at all, and they're all bound together. And we said that they're stuck together because there's a strong nuclear force that's the strongest force that we have that's holding them together, even stronger than the repulsion happening here between the 2 charges. That's what's holding the nucleus together. As you build bigger and bigger atoms and make them heavier, the nucleus gets physically large, where the strong nuclear force can no longer hold it anymore, and so then the electric repulsion takes over and the thing just starts to disintegrate. We call that radiation. And of course, when those radioactive bits hit you and they hit your cells, they destroy your tissue on a microscopic level. They destroy your DNA, and that's why you get radiation sickness. That's why radiation's bad. It's like trillions and trillions of little microscopic bullets hitting you and destroying your little chemical nucleotides inside of your DNA. So this is the nucleus. And surrounding this nucleus is what we call electrons. So I'm going to draw 2 of them here, and they have negative charge. So the protons have exactly the same charge as the electron, except they're opposite, right? One of them's positive, one of them's negative. And the story goes that these electrons are orbiting the nucleus, right? And it's a good model to have. I'm not saying throw this model in the trash can. I think of this model myself in certain situations. But what you're going to find is that as you learn more and more about chemistry, and as you learn more and more about physics, this model of the atom, it just isn't true. Because electrons are not really little balls like this. Protons also are not really little balls like this, but that's another story for another day. But these electrons do have what we call angular momentum when we talk about quantum mechanics, and that's why in the early days they thought they physically rotated like little balls, like little solar systems. Right, they go around like this. But this is it is a good model to have in your mind in the beginning, because you can understand that these electrons are in a certain orbit, which is a certain distance away from the nucleus. And what we now know is that if we pump energy into this thing, like if we heat it up, then these electrons will go out to a higher orbit, right? And when they decay back down, they're going to release a photon, which is light. So whenever it's a useful model to have, because when you put a piece of metal in a campfire and pull it out and it's glowing, the reason it's glowing is because the fire put energy into the metal, into the atoms. That energy goes into the electrons, which they kick them up into higher orbits. The energy has to go somewhere. It go into these very light electrons, which gets kicked up into higher orbits. Okay? And then when eventually one of these electrons falls back down, when it falls back down, it releases a photon of light. And that photon of light is what you see. So everything that glows, glow-in-the-dark sticker, glow-in-the-dark, anything really that emits light of any kind, it's LED, lasers, it's because of electrons moving around, because that's what's basically doing it. Now that's more of a physics thing, but we also use that kind of thing in chemistry as well when you get to the more advanced material. All right, but as I said, this is not really the right model of the atom. What is the right model? Nobody really knows, but I will tell you something a little bit closer to the truth. These electrons, right, that we're going to learn about later, and also the protons and the neutrons too. We'll save that for later. These electrons, they're really wave-like things, right? They're wave-like entities, and we know this because we've done lots of experiments with electrons. They behave more like waves than they do anything else. We don't notice it because we're so gigantic compared to these tiny little waves, so we don't notice the wavy nature of electrons or protons or anything else, but it's true. They all have a wave-like character. Light waves also have a particle-like character, and electrons are matter, but they also have a wave-like character. So everything has a wave-like character and a particle-like character. Everything does. Everything you've ever encountered in your whole life is basically a wave at its core that can also look like what we call a particle to us, okay? So if I had to draw something a little bit closer to what the actual structure of the atom is, and this is not going to be right either, okay? So please just keep that in mind. Then what I would say is, and not just what I would say, well, what we know is that the nucleus, yes, has these positive protons and so on, but the electrons are not really little balls that are just orbiting around here. The electrons are really a wave. And the reason that they're this far away is because this wave has to close in on itself. So it's like a wave that goes around and it has to close in on itself to be a wave. So I drew like this lopsided potato thing, but you have to, in your mind, imagine it vibrating. It's like goo, 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 goo. It's like vibrating like a string, right? Like a string that you tie to the wall. If you tie a string to the wall and you start vibrating it, you can set it up where it's like goo, 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 goo. It's like doing that little wavy thing. That's called a standing wave, because you have one wave going toward the wall, one wave bouncing back from the wall, and they kind of interact, and they do that. If you set it up right, you can get that standing wave oscillation thing happening, and as long as you keep doing it, it keeps making that effect happen. Electrons are more like a wave, and the reason that they have to be a certain distance away from the nucleus is because they have to form a closed wave pattern, otherwise they're not an electron anymore. And so again, you have to imagine it vibrating like kind of like this. And when I put energy into this thing to kick it out into a higher orbit, then what I'm doing is I'm making more wiggles in the electron out here. So maybe it's doing something like this a little farther away, but it still has to close in on itself. That's what a higher energy electron looks like. And then of course, when it decays back down, because it is attracted to the nucleus, right? So it does want to decay back down, it goes back into this state. But it can't get into a lower state than this because it has to form that standing wave thing in order to be called an electron. Okay, now, I told you all education was a series of lies. I don't expect you to remember this or know this or even care about this right now, because we're just starting our path on chemistry. But like I said, I want to break down your barriers so that you know that stuff is coming that's going to blow your mind. I want to blow your mind a little sooner. So stick with me and I'll talk to you about something further. This even really isn't a great model of the atom, okay? Even though it's pretty good, it's much, much closer to the quantum mechanical nature of the electron and the atom, okay? It's much, much closer because it really does convey the wave nature of what's going on. But the question that you get over and over and over again is, if electrons are negative and protons are positive, which are in the nucleus, and they're attracting, why doesn't the electron just slam into the nucleus and just live there? Like, why do we have this orbiting business at all? Well, when I phrased the question, you see how I put my fist here and I said, the electron is negative and it's right here, and the protons are positive and the right, and I put my fist up like this, right? Because you see, subconsciously, I want to believe that these electrons are little balls, but they're not little balls. These electrons are extended things called waves. This whole thing is the electron, not just this little part of it. The whole thing is what we call an electron. Let me ask you a question. If you're at the beach and you watch the waves come into the beach, and I ask you, where is the wave? Then you're going to point to the crest of the wave and you're going to say it's right there. That's it. But actually, if the crest is right here, what if you go down from the crest a little bit? Is this part also the wave? Or is it only the top part? Or how about on the other side of the crest, when it comes down over here, is this part also the wave? Well, yeah, it's all part of the wave. So where's the wave? The wave is not something that is right here. It's an extended thing. Because a wave by nature is an extended thing. In fact, the whole ocean is covered in water. And you could make an argument that the wave really is the entire surface of the ocean. It's just there's a localized crest right here, but the wave really goes down and extends throughout the entire surface of the ocean. So really, if the wave, work with me here, if the wave represented where a particle would be if you measure it, then where the wave is big, you would expect the particle to be mostly there. But where the wave is small, then you would not expect to see the particle at the small parts of the wave. If you adopt that model, then what you come up with is that the whole surface is really the electron, is the wave. But where the wave is a maximum there is just the most probable location for what we call the electron. Because when we measure the electron, we say it's there. When we measure the electron again, it's going to be in a different location, right there. Now, in the old theory, we say that's because the electron's just going around and around and around. And you might measure it, and it might be in different locations, but it's much more complex than that. Actually, the electron is a wave that extends all throughout space. It has a most probable location in this orbit around the atom, but it can be in different locations, and if you measure it enough times, you will measure that it is not always in this nice little dotted line, which we call an orbit. And it's not going to always be in this nice little location here. Sometimes it's going to be a little farther away. Sometimes it's going to be a little closer to the nucleus. But its most probable location would be at this distance, the red line here, a distance away from the nucleus. So I come back to my original question. Why doesn't the electron just crash into the atom? Or the nucleus, because the nucleus is positive, the electron's negative. Why doesn't it just smash in and live there? They're attracted to each other. These are deep questions that I don't want to say they don't have answers. We know why, but they're not easy answers. There's a lot of reasons why that doesn't happen. One of them is because of when we learn quantum mechanics later, you're going to learn something called the Heisenberg uncertainty principle. Basically, it says that you cannot know the position and the velocity, also there's energy wrapped in there, a different way to formulate it, of a particle at any given time. Right? And if the electron crashes in onto the nucleus, then you're going to know with very high certainty where that electron is. It's on the nucleus. And so that means it has to be moving very, very, very fast, which means it's going to escape the nucleus. Because you cannot have a zero position and a zero velocity of anything all the time. It violates uncertainty in quantum mechanics. I told you this will bake your noodle because this is not common sense. You don't see this happening, but this is true of electrons. So it cannot live on the nucleus because if it does, we would know exactly where it was. And if we know exactly where it was, then it violates uncertainty because then it would have to have a very high velocity, in which case it would, or momentum, it would have to escape the nucleus again, right? And the last thing I will tell you is to blow your mind a little bit further, that this thing here, I've drawn it as a two-dimensional little wavy thing. Remember, atoms are three-dimensional things. So when I'm talking about the wave nature of the electron, it's not just a dotted line that's around that's vibrating. It's a three-dimensional thing, three-dimensional spherical thing. In fact, the innermost electrons to atoms all have a spherical, what we call a spherical distribution, a spherical wave function, right? So the wave nature of it is spherical in its shape. And actually, it turns out that these waves, you might say, what do they represent? Okay, you tell me the electron's a wave. What's waving and what does it represent? Well, what we say in quantum mechanics is that an electron is represented by a wave function, which is a wavy thing, and we can do calculations with that wave function, and the wave function represents the probability of where the electron will be if you measure its location. In other words, if you set up a detector and you measure the location, you're going to see where the electron is. If you set up a detector and try to measure it, maybe it's here. And then you do another experiment and you find out the electron's here. Maybe it's here, maybe it's here. Every time you do the experiment, you find a new location for the electron. But the wave nature of the electron is extended in space, and every time you measure it, you get a different location, but the shape of the wave function surrounding the atom tells you where you're likely to find the electron. It tells you where you're likely to find the electron. So one thing we're going to learn about later is if this is the distance away from the nucleus of an atom, and this is the probability, I'll put P, the probability of finding the electron there, and right here is the nucleus, then what happens is you have a curve that looks something like this. This is the probability of finding an electron surrounding the hydrogen atom. And notice there is a peak right here. We call this peak A, which is, or A naught, which is the Bohr radius, because this is the Bohr model of the atom. We'll talk about, you know, it's when I say Bohr, it's B-O-H-R, not like bored, it's B-O-H-R. And so what we find out is because of the probabilistic nature of quantum mechanics, and because these things are waves, and because like on the surface of the ocean, the wave is extended everywhere, right? Then there really is a probability that the electron will be really, really far away. Think about the surface of the ocean. The wave crest is near the shore, but the ocean extends way, thousands of miles away. And if the crest of the wave is an indirect measurement of the probability of finding an electron when you measure it, then you're much more likely to measure it right here, which is what we draw, this dotted line called the Bohr radius. We say the electron's here. But actually, if you measure it again, it might be a little closer to the nucleus, because the nucleus is right here at the origin. It might be really close to the nucleus, but it's going to be a lower probability of finding it here. It might be really far away from the nucleus, but it's going to be a low probability of finding it there. I might measure the electron position around an atom, and because this thing never gets to zero, I have a small probability of finding that electron over near the nearest star system, Proxima Centauri, 4 light years away. It has a very small probability of being anywhere in the universe. Way over there, millions of light years away, because this mathematical function never gets to zero. So there's always a small chance of it being over there. And there's a small chance that the electron will be found nearer and nearer and nearer. And actually, this curve does not hit exactly zero. There is a very small probability that you will find the electron on top of the nucleus. So when I asked you the question, I said, hey, a lot of people ask me, why doesn't it just crash into the nucleus? And I told you, I said, well, actually, if it did that, then it would violate uncertainty, and so you never find it there. I lied to you again. Actually, there is a small probability of the electron being in the location of the nucleus. It's very small. But if it happens, then what happens is something called electron capture. You don't need to know this for chemistry, but it's just something to satisfy, hopefully, your curiosity. Is basically a proton can absorb the innermost electron of an atom and turn into a neutron by absorbing an electron. And in that process, it releases another particle called a neutrino. This is way beyond the scope of chemistry, okay? I'm just mostly telling you this for completeness. People want to know, why don't they crash in? Okay, I'm telling you, it's possible for that electron to have a position on top of the nucleus. It's incredibly small to happen, but it can happen. And when it does happen, the proton in the nucleus absorbs it, turns into a neutron, and releases a neutrino, which is another type of radiation. It's another particle that can come on out. There's a whole universe of these little particles that are way beyond the scope of this, but that's called electron capture. So I told you, education was a series of lies. First, we say, hey, let's go ahead and do some experiments. And let's see what this radioactive stuff means. There's 3 kinds of particles that come out. One's got positive charge, one's got negative charge, and one's got no charge at all. And we can learn something from trying to deflect them with these plates, and we can figure out the charges. And then we say, all right, the positive and negative charges, maybe they comprise what atoms really are. So let's say that they're just evenly distributed there. That's our first model. Let's test it and see if it's true. How are we going to do it? We're going to shoot a bunch of alpha particles, which are positive charges, high mass, at a very thin target. But surprisingly, they bounce off. So it can't be this model, because if it was this model, we would never get anything bouncing back at us, not with this magnitude here. So we say instead of that, maybe the nucleus is concentrated with the positive charge, and maybe the atom is mostly empty space, so whenever the incoming particle hits the nucleus or gets close to it, it bounces and ricochets back. That's probably closer to the truth. So then we discover, or we write down this thing called the Bohr model of the atom, where the nucleus has the protons and the neutrons. The protons are all positive and the neutrons are neutral. Surrounding that, we have these electrons and negative charges, and that makes perfect sense because we have the planets in the solar system and they go around the sun. So by analogy, maybe the electrons just go around and around like little solar systems. Everybody's happy. And then they finally say, well, wait a minute. Actually, if we shoot a beam of electrons at a double slit and we do a double slit experiment, they actually behave like waves more than they do behave like particles, because when we shoot light and we do these experiments with light, we see an interference pattern between the crest and the trough of the light waves. But when we do the same exact experiment with electrons, which we think are particles, we actually see a light and dark pattern of interference. So we suspect that electrons are also waves. So then they develop this whole theory called quantum mechanics and say, well, wait a minute, if these things are waves, then they're not just at one location. Just like a water wave near the shore is not at one location, it's just got a range of locations. Whereas the wave is everywhere, it's just a maximum right there. Maybe electrons are like that. So then maybe they're not just these little balls orbiting, maybe they're vibrating waves that are surrounding the atom. And if that's the case and you go through the quantum mechanics, you can, with a lot of math, come up with a plot that looks like this that shows you the probability of finding an electron surrounding an atom. And what you'll see is there is a maximum probability, which is where we say the electron orbits. It most likely is going to be found in the orbital location. That's why we thought that they orbit in that orbit when we did the original calculations. That was its most probable location. But the electron can be found farther away. In fact, the electron can be found across the universe with a very small probability. And the electron can be found closer to the nucleus also with a very small probability. In fact, the electron can be found inside the nucleus with a vanishingly, incredibly small probability. But if that happens, the proton's going to suck it up, turn into a neutron, and radiate out something called a neutrino. It's a radioactive process. So, education is a series of lies. And I'm sure that as you learn the things that I'm trying to teach you, and you go on and discover the next best thing and the next theory and the next experimental result, right? That you are going to prove some of the things that I have said wrong. I hope you do, because it's the only way that we go farther in this world. I could have stopped this lesson in the beginning and just talked about the discovery of the particles, and that's cool. But what I really wanted to do is share with you the path and the journey of where we are today. There is a whole lot of math that goes into this. This stuff I'm drawing on the board, it's not a result of just somebody saying, oh, maybe it's like this. It's a mathematical model with equations that we can predict things from. And quantum mechanics is our most accurate theory. It is very, very accurate to many, many decimal places. And without quantum mechanics, we could not build computers, we couldn't build phones, we couldn't build anything with modern technology. So we're reasonably sure it's correct. Doesn't mean it's complete. It may not be complete, but we're reasonably sure that it's very close to being what actually matter is made of. So I'd like you to watch this a few times and then follow me on to the next lesson. We're going to get back more into the realm of chemistry and how the chemical reactions happen as we move forward with talking about the atom. Learn anything at mathandscience.com.